So we're going to get started. It's just a little afternoon. Thanks for coming. It's nice to see some new faces and faces at all. So you're all my favorite people right now. So we're lucky today to have another great biology graduate student association and department seminar from Dr. Schneider. And first, I'm just going to give a quick land acknowledgement to get us started as we do. So we would like to respectfully acknowledge the island of Newfoundland as the ancestral homeland of the Mi'kmaq and Beothuk. We also recognize the Innu of Nunatsiavut and Nunaktavut and the Innu of Nunatsiavut and their ancestors as the original people of Labrador. We strive for respectful and equitable partnerships with all the people of this province as we work towards true reconciliation and honor this beautiful land together. So we have Dr. David Schneider here today to give us a talk about statistics. Now, Dr. Schneider is from the Department of Ocean Sciences at MUN. He's been at MUN for almost 40 years. Before that, he was in Rhode Island, California, Massachusetts, with forays abroad to Panama, South Africa, and New Zealand. But don't let the ocean science affiliation fool you. Dr. Schneider's been involved in a lot of different studies and systems, and probably listed as a co-author on many, but a sort of silent contributor to many more. Pretty much for any memorial student who's taken his quant methods course, something you do was probably informed by something that you heard in that class. So Dr. Schneider's co-authored papers across systems from cod to caribou, but today we're going to talk about the challenges, opportunities, and progress in statistical science, and I think you're all in for a treat, whether you already know Dr. Schneider or not. So without further ado, let's let the real talking begin.
So I'd like to thank you for showing up today. I realize that some of you got to miss a quiz today by coming here, so that was a little extra side thing for some of you. I recognize some faces here, and I recognize a lot of other faces as well. To be a little clearer, I will do what I'm supposed to do and drop the mask. So the odyssey that I started with statistics was a side thing. I never thought I would be ending up teaching statistics. It started when I took a stats course with Robert Sokol as a graduate student. And as a graduate student, we did nothing else that term except for one book. We went through the book. And that's the first edition up there with Sokol. And that's what you learn, how to do frequentist statistics from Robert Sokol, who wrote the book. I've also got a picture up here of John Nelder, and John Nelder is going to be pretty much a person who's part of this talk. I'm going to use a paper that he wrote on statistical science, and that's going to be an important part of the paper, and it'll be a little bit of a dialogue between him and me, given that he is no longer with us, kind of posthumous, if you will. Another important event in my life was after coming to MUN, there was a TA working with me named Chris Beidick. He had a master's in statistics, and my experience was working with the general linear model under my research. But the teaching I did was out of the book, Sokol and Rolfe. So there was a split part of my life. And Chris, that's Chris Beidick there, third picture over, Chris said, I bet you can't teach the general linear model to undergraduates. And I said, I'll take you up on that. So that was about 20 years ago. The general linear model was what I used routinely in research, but it was not part of the teaching activity. And the general linear model is very much learn to write the model so that people who've taken the course with me will know I do this again and again. What's the response variable? What's the explanatory variable? What do you want to know? So there I am today after this odyssey. And I'm going to start with quotes from John Nelder. And the first one is right there, and I'll let you just read it yourselves. Now, this is a deliberately provocative paper, and so you see something very provocative right away, which is the theory of significance testing. He's put the idea out there that he developed over the course of his life that there's more to life than hypothesis testing and p-values. So flotsam. Here's a list of flotsam from Michael Crawley, and he often uh, uh, he went through two textbook renditions. One was a process called GLIM, which was a software, and later he moved to R. But he's been working with statistics quite a lot, and you can see that he's focused on a model. That's number one. He thinks a lot about the sampling errors. That's number two. He thinks about the scale of measurement. I really like that. I'm a scientist. I think about the scale of the measurements I take, not just numbers. Uh, and he also mentions dimensional homogeneity, a concept that you know if you've seen if you did the course with me. I think that's an important part of how we think, even though it's often done just in physics. He considers the ideal transformation, and that I'll kind of skip that for a moment and move on to the seventh one. Too much emphasis on hypothesis testing. So he's in the same frame of mind as Melvin. Okay, more flotsam. I'm going to say that searching for the right test is a carryover of the p-value culture flotsam. And there's a series of things we do in that p-value culture. The first is we try to identify a test by name. We want to check the assumptions, and we try to do that beforehand, which turns out to be incorrect. We use automated routines that sort through, give us a p-value, and that's when we stop. We have a p-value. I want to contrast that with teaching the general linear model, which is what's the response variable, what's the explanatory variable. We write the model. It turns out to be a challenge with undergraduates because they're not used to thinking that way. So the course develops over time where the students learn to response explanatory. Oh, I can do that. I can write a regression without having to think of the name of the test. I introduced a model checking route, which you'll see later. And if we have an error structure, like the normal error structure, which is not appropriate, then we take action. We can do what students already know in the course with me this year. We can do a randomization test, or we can change the error structure. And I will talk about that only briefly today. And at the end, we're interested in the model parameters, the effect sizes. What effects did we find? Two means, slope, those matter. And I'll come back to that again as well. Here's some advice that I saw back a long time ago on teaching stats. It served me well. Group activities as much as I can. Open book examinations. This is often new for people. It's a little stressful at first because you don't have to memorize things, but they catch on quickly. I try not to use timed examinations, although that's a challenge. I often give students more time later. Students work at very different paces. There's a few themes that I use again and again, and I try to have frequent work. So the students with me this year, or you've taken the course, you know this, you have something new every week. Repeated contact with the material is how learning occurs. And try to use a bit of humor. So here's a cartoon, outlier on the left, and theory is wrong instead of the outlier. And I'll show a few more cartoons later. Okay, here is so this was a talk I gave in 2007 while I was on sabbatical at the Bodega Marine Lab, and the focus was on poor practices. And here's a tour itinerary. I won't go into this today other than to say that the focus here was on problems that I learned along the way that are probably not good ways to do statistics. I'll move on quickly. Here's some conflicting advice, and I'll let you read them in sequence. So we start out with a rather self-assured physicist named Rutherford. We move on to R.A. Fisher, who developed a lot of the techniques we use today. And then we have somebody disagreeing with Fisher adamantly. Here are the promised cartoons. We have King Kong taking on Godzilla. Uh, and I'm going to turn that into a new one. We have King Kong tossing Bayesian lassos. What is that? And Godzilla shoots back with ridge regressions. What is that? Everyone's confused by this. Well, they're fine techniques, but for the beginner, very confusing. And so force King Kong back. Here's the talk that I gave here, and the focus of this talk 2 years ago was all the things that I used to do that I found out were wrong. So there's a long list of things that I was doing all along the way that were wrong. And so this talk was a summary of the things that I had learned along the way, where I was doing things that I had found out were not good ideas or were outright bad ideas. Uh, Tour of things I once believed or once did myself. Mythical attributions, I won't spend much time on that. Mythical practices, like, for example, checking for normality of your data. Well, it turns out the assumptions are about the residuals. That is the difference between the data and the model, not the data. So if we check the data, we always end up with an answer that's irrelevant to what the assumptions are. We cannot check the assumptions until after we have estimated the slope and gotten the residuals from the line. So that's a mythical practice. Yeah, it's widespread in literature, and it's even reinforced in some packages. Misconceptions, mistaken beliefs, misinterpretations. The one that people hear from me from time to time is Bayes' theorem. Bayes didn't write it, Laplace did, but it's gotten locked onto Bayes, and there's no evidence that Bayes. You can, we'll bet you $20. You cannot find Bayes' theorem in Bayes' publications. $20. If you could do that, you get $20. Because I've tried, I can't find it. But if you could do it, great. So that's a misinterpretation. Malpractice, when we transform data to ranks, I'm going to call that statistical malpractice. We're removing information that we can use. And it matters. Uh, and these misinformations or false beliefs tend to spread. And so we have something called the p-value culture resulting from that. Okay, on to today. So there's a background there of where I'm coming from over, good heavens, 40 years, we said. Wow. Okay. Here is an outline of Nelder's paper, and he's deliberately polemical and controversial. He calls, I'm going to start with a definition of statistical science that he came up with. I'm going to move on to the next part of his paper, which is why we need it. And then I'll move on to what needs to be done. So this is organized around a paper by Nelder, and there'll be a little bit of a comment by me along the way. Okay, another quote from Nelder. He's going to define statistical science for us. So the key words here are deductive for math, inductive for statistics, and real-world data. Now, this is Nelder's contribution, a huge contribution. The general linear model, generalized linear model, is the workhorse for research scientists in R. He wrote the book along with a colleague, McCullough. He was also a bird watcher, so I see at least one bird watcher in the audience. There's probably some more. And so he came up with, when he retired, he went on to other things like debunking these false citations of rare birds. The guy would catch a bird, taxiderm it, create a history, and make it look like a rarity that he discovered somewhere in England. Okay, moving on to some more quotes from Nelder. What is statistical science? And fairly forward comment here, directed to his colleagues, the idea that if you're going to advise people to do statistics, you need to learn the scientific method. It's a pretty radical idea for a statistician. And finally, he says we should rename this statistical science. The center word is science, not statistics. Statistical science. And he's going to talk about the cycle of design, execute, and analyze. So I'll walk you through that quickly. First, thing at the top is what we tend to do now with a textbook approach. We put together the data in a model, we select the model, summarize conclusions, and stop at the p-value. The innovation here is that we start with the model and the data, fit the model. Is the fit satisfactory? We're assuming an error model. Is it correct? And before we move on to the next step, we need to make sure we have it right. And so when you take the course with me, you see that you learn how to do this model checking step. If satisfactory, we move on to summarizing, including effect sizes. So there's Nelder's contribution to how we should teach statistics. And it turns out I learned this kind of on my own, the hard way, by developing a recipe and modified over time. But I felt it important to get the assumptions up front and checked at the beginning. So I'll add a little bit more. What is statistical science? We have Nelder's definition to add a bit more. It is something that is not a set of named tests, which is what I learned. The textbook I learned from was a set of named tests. It's how to write the model and then interpret the parameters. And I'm going to talk about parameters that can be interpreted by us as scientists, whether we're chemists, physicists, biochemists, doesn't matter. We're going to talk about cod mortality as 6.6 cod percent per year. That's a very high mortality resulting in an unsustainable fishery here in Newfoundland. Should be around 0.2, 20% per year. Also an error model. Mostly the course they do is a normal error model. That's the general linear model, but students are exposed to the generalized linear model, which has non-normal errors. And because they've learned how to write the model, they can make that transfer fairly readily. Here's what I came up with over about 20 years, a way of doing a stepwise approach, which starts with constructing the model. That's the first step. Writing it out, learning how to write it out. Executing it, which is part of the labs we do. And then evaluating this model checking loop. So that's an important part of the early steps. It took about 20 years to arrive at this. It seems simple, straightforward. Oh yeah, of course. But it took about 20 years to work this out. That's by working with students. You try something out. If something works, something doesn't, you modify it. So things have been modified working with students over 20 years. And so there's a lot of detail buried in behind here. So this is beyond. This goes past Nelder, who never really taught. As far as I know, he was at a research station, and so his primary thing was advising agricultural scientists. Okay, here's the Flotsam quote again, and I'm going to walk through Nelder's list of why we need statistical science. And the first is the p-value culture, and trying to identify it, show why it's not scientific, and then we can move on from there. So a quote at the bottom from the president of the American Statistical Association in regard to why do we teach p-values. And his answer, you see, was points at what we as people who teach statistics need to think about a lot, which is how does it get maintained? It gets maintained by us teaching out of a textbook that has p-values. So that's a hard step. The even harder step is now what, and we'll get to that. So the p-value culture. There's other reasons we teach p-values. They're throughout the literature. So in order to understand the literature, you really have to know what a p-value is, and it's often misinterpreted. Students need to understand the literature, and there are an awful lot of really nice texts out there with lots of worked examples, and they're all aimed at the p-value. So we've got these wonderful texts, and typically we're trying to do a lot of things. We're trying to get a research program going, so we do the stats, but it's really nice to have a text that we can do this out of. So this propagates the p-values. Flotsam, good heavens. So here's a quote by somebody who I will eventually call an evidentialist. He works in the health sciences. He's at Stanford right now, and he calls it the p-value fallacy. This is a hard one to unpack, so I probably won't attempt it today. But the key ideas here is that we're trying to do something that gives you a long-run probability, and we're presenting it as evidence. That's what's packed in this. We're presenting something that's meant for one thing. What's the long-run probability? Presenting it as evidence. It's not. There's remedies. The first step was the American Statistical Association. This is almost 20 years after Nelda. The American Statistical Association said in a highly scrutinized uh, publication by their own peers before it even appeared in the American Statistician, they basically said, we need to use this with caution. We have to be very careful about this because of all the things that happen that are misuses of the p-value. If we use p-values and we have a large sample size, they're almost always significant, but the effect sizes are tiny. If we use p-values with small sample sizes, then there could be something going on there, but we can only detect a huge effect size, and so we miss things for small samples. So sample size drives the errors that happen when we use p-values as evidence. 3 years later, the American Statistical Association came around and said, we need to not use p-values anymore. They finally did it. I think everybody's surprised. They finally came together and said, no more p-values. This is a tremendous help for those of us who teach, because who am I? I say no p-values. Well, oh yeah, Dr. Schneider says so. Well, who's that? Anyway, but if we have the American Statistical Association, then I can point at this as this is a consensus by statisticians. So this is important to development. Aki information criteria are sometimes used as a replacement for p-values. They're not really. They're actually a measure of evidence. They're a Baker likelihood ratio, and they have nothing to do with p-values. It's true, but they also have nothing to do with the sort of models that are routinely used by research scientists. I won't spend too much longer on that. It's a valid way of doing things, but I'm going to call it a likelihood approach and fold it in later to what I do. And the likelihood approach is due to Richard Royal, who wrote a book in 1997. I met one of his students at a meeting, and we talked about the Royal book. We both thought it was a wonderful book. She was a student of Royal, but I just read the book. And she said that Royal thought that since the book really didn't catch on, he considered himself a failure. It didn't catch on. There's another source of this evidence ratio called Jeffries. That's another textbook by a geologist. It never caught on. And I'm going to call the direct likelihood approach evidentialist because of the person who reviewed the book. And I'll come to that later. So I've also mentioned priorist inference. I'm going to call it priorist because that's what it is. We take a prior probability, we apply a likelihood, we get a posterior probability. And the eponym is wrong, and why find a new eponym? Let's name it after somebody else, like Keynes or Laplace. Maybe we should just call it what it is, priorist. So I'm going to be a little outrageous here and call it priorist, because that's what it is. Okay, here are Crawley's comments again. I'll move on because you've seen those. And they have to do with the idea that we report whether it's not something is significant or not. We lose all the information that's in the time linear estimate. So this has been around a long time, the idea that you report the p-value, not whether it's above or below 5%. And Crawley addresses that as well. So Nelder, no, against the idea of reporting significance or not, report the number. The approach that the American Statistical Association recommended is report effect sizes. So what's effect size? If we have two means, how different are they? That's the effect size, and they have units. Or we have a slope. The rate of change of one variable with another has units, so that's another effect size. And so this is a highly cited, you can see, a review article which really establishes the idea of how we do effect sizes. There are whole books written on it by now. Here's another example. So here's the classic data set from Galton showing heights of sons and fathers, the regression. And effect sizes are not numbers, 0.52. I'm going to say that they are numbers with units, which in this case are the centimeters in height of the sons in one class relative to the fathers. It's less. There's a tendency for what Galton called regression to the mean here. Uh, and this uh, captures what happens that we sort of know about, which is that there's a familial component to height. There are a lot of other factors too, but there is a familial component. So I'm going to say that this has units, and the units are centimeters or inches. They're certainly not kilometers, which again illustrates the idea that we should not. We need to pay attention to our units. Um, Multiple comparison tests. These are really ubiquitous. They have a certain objectivity to them. I've got 5 means, and I want to know which one. And I did a test, and there's a difference in the means. I know that, and I want to know which one it was, but I don't know which one it was. So I used the Tubi comparison or Chaffee comparison. There's a whole series of these things we do. They have a certain logic to them because they're being objective. I've found in working with students, if you ask the student about the data, they'll say, oh, yeah, well, I did an experiment because I expected the treatment to differ from the control. So right away, we've already got a setup there. And I find that's true again and again with students and colleagues when I talk to them. There's always a purpose for the experiment, and the purpose brings with it an a priori comparison, a control versus this treatment, or two treatments that we expect to differ. So I'm going to call that an a priori approach where we test those instead of the a posteriori, after the fact approach, where we sort through all the means in a objective sort of way and find the ones that differ after the fact. We usually know enough to do a good a priori test. There's some other technical reasons they're good too. Distribution-free methods, these have a real appeal because if we have the assumptions not met, well, the solution is to do these tests that get rid of the assumptions. Well, they also get rid of the information in the data. And we have no more units, we have no more effect sizes, we're not dealing with means, we're not even dealing with medians or modes. All we get is a p-value from these. That's it. Just a p-value, there's nothing else. And so we lose a lot when we move to these rank-based tests that throw away our information and turn it into a p-value, and that's it. So Nelder does a paragraph or two on that. Here's a quote. Again, trying to be dramatic. Okay, the last one that he lists, second to last that he lists is untrue or uh, incorrect models. There's a statistical um, description he provides, which really is beyond me, about why this particular maximum likelihood thing is not the same as this one, and we should not get them confused. But he also refers to hypotheses, to null models that are uninteresting. And here's the example: if you have heights of fathers and sons, the null model is of no interest. We know there's a relation, so there's no point in testing it. It's more plausibly might be done on a one-to-one. We might expect a one-to-one relation, something like that. And the students that just saw the presentation just a couple days ago know about what happens when they do that. It's not one-to-one either. It's very tightly closed around 0.5. But at least it's a more plausible alternative than the null. Okay, what needs to be done? The first is here's a whole list of things about what needs to be done. I'm going to spend most of my time on sorting out the modes of inference. And here's another quote. So a fairly dramatic way of stating that There's more than two modes of interest. There's three, and he's great. He's going to call himself he's going to call himself likelihood type, and I'm going to call it evidentialist because that's what's been named in the literature. There's the $20 bet. Oh, well, let's not spend too much time on this. There's the person who first wrote it. There's the person who proved it. It's the same person that did the treatise on money. His first treatise was on probability, then he did something on money. So I'm going to. What Bayes really did do something. He put probabilistic limits on an unknown number. So it's nice, confidence limit back from the 18th century. Okay, sorting out modes of interest. I'm going to list three of them, and one I'm going to call evidentialist because of the review of the Royal Book. It was by Victoria Veland and a co-author, and they did a review of the book in 1997 when it came out, and they quite a long review, 3 or 4 pages, where they laid out what was in the book, basically, and they gave it a name, evidentialist, which I think is appropriate. We're going to base our inference on the evidence. The second one I'll talk about is priorist. There it is, the likelihood ratio times the prior uses the posterior probability. Makes sense for monitoring programs. And frequentist, which is what we're used to teaching. And we can use the likelihood ratio to calculate statistics that we see again and again, the G statistic, the F statistic, and get a p-value from the likelihood. So you see this likelihood ratio is really fundamental to everything we do, but it's kind of hidden. And we can back calculate the likelihood ratio from easily obtained statistics like the explained variance. So we have explained variance, we can calculate the likelihood ratio and interpret it. So what is this likelihood ratio? Well, there's a picture of Richard Royal. There's his book. There's the colleague I met at a conference, and she used the name evidentialist for the book. There's a calculation at the top, and if you plug in the numbers for 50% explained variance in a certain sample size, you could say that the alternate is 32 times more likely than the null. That's what students really want. They want the comparison. The p-value thing is kind of off on the side. Okay, once we get there, this one gives us what we want. It's the comparison. If I change it to a 70% explained variance, the likelihood ratio goes up quite a lot with the same sample size. We can now say, with that much explained variance, that the likelihood of the alternate is 500 times more likely than the null. So this is pretty much what we want in science. We want the comparison. And we try to do this comparison with a p-value, we get into trouble. Here's another look at the priorist approach. This is from the Treatise of Probability by Keynes. This is the first one to really write it out this way. Take the prior, multiply by what we call the coefficient of transformation. That is so Bayesian. It's just so Bayesian. But it's buried in the treatise that nobody reads, and you get the posterior probability. So this is what appears in the book by Keynes, and the coefficient of transformation says what the priorist approach is. We're going to transform the prior to a posterior. Jeffries called it a K factor, so that's good too. Maybe we should do that. And the likelihood ratio is buried underneath the F statistics we know about, or underneath the T statistic that we know about. And it's how we get a p-value for the likelihood ratio, by transforming it into a G or an F and getting a p-value. And that's because of R.A. Fisher, who came up with this whole approach. Here's one of his rather bitter quotes. I'll talk about it in a minute. So that's a rather striking quote, but it's not the way to convince anybody of anything. It really isn't. And Fisher was notorious for this, for just for immediately going ballistic when he saw something he didn't like, and spending the next 10 years attacking somebody. So he did that his whole life. Uh, so this is not the way that you move on from p-values uh, with quotes like that. Here's the ASA statement. In 2016, 5,000 quote citations in 5 years. That's 1,000 a year. That's pretty good. And the more recent one is running about 600 per year. So it's being cited a lot, which is good news. It means people are reading it and using it. They're actually using this and saying, the ASA says no p-values. This is important because of referees. Okay, so we've got the case made by Nelder for demolishing the p-value culture, and we've got help from the American Statistical Association after 15 to 20 years, which I hope will make a difference. It seems to have so far. And here's Nelder's quote on what needs to be done. Replace the p-values with measures of effects. That's a quote from Nelder. Play down distribution-free methods. It's not going to get rid of them, but they only give us a p-value, so we're going to kind of back away from those. And we're going to model the errors. And what he means by that is we're going to look at the residuals. If the errors are not, if we don't see conformance to our normal errors, we're going to choose a different error model. So we're going to pay attention to the modeling of errors, choose a different error structure. And of these things that Nelder listed, only the first is addressed by the ASA statements. These other two, discarding most comparisons, playing down distribution, and modeling of errors, were not part of the ASA. So in Nelder's write-up on this, he talks about statistical reviewing and how it's kind of it works pretty well for what it does, but it has some problems from time to time. And from my experience with being asked to do statistical reviews, is it takes a lot of time to do them because you got to read the paper and then actually do some numbers to see if things are right, instead of using your verbal or um, or you're using your information that you know about that field of study. So if you know the field of study, you can make a good critique based on the field of study and your knowledge, see some obvious errors, but the statistics are hard. So I'm going to propose an empirical relation based on my experience, which is that the quality of a statistical review is inversely proportional to the time it requires to do it. And so if it takes very little time, uh, it's probably not very good. That's a purely empirical observation. I can't prove it. Okay, Delder lists helping journal editors. He doesn't have too much to say about this, but I can offer some things to say about this. Now, Delder moves away from this really quickly and talks about political things. I didn't know what he meant by that. He seemed to not want to talk about it. My experience with doing a lot of reviews in life is that you can easily get conflicting statistical assessments. And I'll tell you a story about a consulting thing that I did in Hawaii. I showed up. I was the more scientifically oriented statistician, and the other person was more, he was another biologist, but he was more oriented toward the stats. And one of the senior people had said, don't worry about those statisticians. They're not going to, don't worry about what they're going to say we have to do. Because after a while, they're going to get into a fight. And well, we just let them do that. So when I heard that comment, I went over to talk to John. I said, John, I'd like to tell you what I heard. Uh, so, and he said, oh, yeah, right. Yeah, I heard that too. So I said, well, why don't you and I just think about, well, let's compare notes on what we believe. Let's compare notes on what we believe. And so that we're not, going, ignoring that. He said, yeah, we'll do that. So the approach we both took was if we offered advice and it was the other person wasn't quite sure it was in their experience, we'd talk about it later and try to square it up. So I'm offering some dialogue with John Miller. Here's another reason that he thinks it's hard to get reviewers to change their views. sorry, editors, those are journal editors. They really can't do too much about the conflicting reviews. He talks about software. I'll move on quickly. And here's some more advice about teaching statistics. Embed courses from Delder, embed courses into the experimental cycle. You saw that. Teach the power of the experimental method. That's pretty radical for a statistician to say that. And he really thinks that students should carry out an experiment. This is my final, I think, take on how we can do um, uh, work with students in doing their analyses. And it works quite well based on 20 years experience. I won't go into detail. Educating colleagues, we've got this, that really helps. Uh, P-values were replaced by likelihood ratios by the Intergovernmental Program on Climate Change. They refuse to use p-values. They use likelihood ratios. We have a problem of what's a good likelihood ratio. I'll let you think about that. It's not settled. So here's a summary, and it's based on starting with John Elder. You saw him have a big plan at the beginning, and then more and more me at the end. So likelihood ratios are not a measure of evidence. Likelihood ratios measure the evidence. P-values do not. Likelihood ratios, we need to report them as well as the number of observations. You saw the reason why the abuse occurs. Effect sizes are important, and we should use units on them because we're scientists. 3 modes of inference and justify them. Why are we doing evidentialist? Why are we doing frequentist? Why are we doing priorist? And finally, just at the end, as a side thing, report typo and error, not significance. So that's the final take-home message. Thank you very much. So 12:43 and a question.
Yeah, thanks so much for the talk. You kind of addressed it on the second last slide, my question, but I'm wondering either from like an education perspective or doing science or for editors or reviewers, thresholds a good thing? Are they helpful in any of those contexts, whether it's like a p-value threshold or a likelihood ratio threshold?
I'll sort of I'll take that as a start point and move from there. So we got into trouble with thresholds with the p-value. In fact, Fisher himself didn't use thresholds. He had categories, 10% or less, 10% or greater p-value, don't even bother. 5 to 10% maybe something going on. 5 to 1% some evidence, or he'll call it significant. He can say evidence, some significance, and then really good, less than 1%. So those are Fisher's categories. Namath and Pearcey came along and used a decision theoretic approach where we set the alpha beforehand, 1937, and things have gone in a certain direction ever since then by setting it. So that's the bad example. So when asked about this, you saw me sort of back away from that, right? And that was the reason I did it. I could use the IPCC ones. I could use Jeffries as well. And I did a survey of students in class about 4 years ago, toward the end, asked them what they thought was no evidence, some evidence, good evidence, strong evidence, and they came up with uh, no evidence less than 10, around 20 times likely, 20 times more likely, some evidence more than 20 times more likely, good evidence, strong evidence around 500 times more likely, because they'd seen a lot of likelihood ratios at that point. So that doesn't answer the. I think it answers the question kind of indirectly. We got into trouble once. Let's try not to get in trouble again. But everybody, I'm asked that again and again. Well, what's good and what's not? And this comes from colleagues as well as students. So I think there's something about us. We just need some standard, something like that. The 20 times more likely is the flip from the 5% pretty closely. But it doesn't match. If you get a p-value of, they do not match 1 to 1. You'll get different answers. Yeah.
So publishing papers in the future will become increasingly more difficult to publish them if you're using p-values as your statistical approach rather than likelihood ratios.
It's an interesting question. If we take Nelder seriously, demolish the p-value culture, that would be one outcome. is that we would see maybe a swing the other way. However, I work with biochemists. There's always some biochemists who show up in the concourse, uh, and they're working with animals, with animal care protocols. And if you're in the health sciences, we also have protocols there because if you're anything having to do with people, you've got to show that your experiment is not doomed to failure by an inadequate sample size. And the way you do that is you set criteria for type 1 error, typically around 5%. So when you turn in a proposal to work on digestion, and it's going to be in those little pigs, or on rats, or if you're in health sciences and you're going to take blood samples from people and get their consent, you need in your proposal to do the calculations based upon a type 1 error. So I don't see them disappearing completely, despite the demolished approach, which I think was generated by the Neiman Pearson fixed criteria. Uh, that's only a guess about the future. From my experience with working with biochemists, when their supervisors turn in the proposal, they have to do the power calculations. That is, show that the experiment, if that effect size is big, I can detect it with 20 piggies, that kind of thing. Yeah,
Yeah, thanks for the talk, Dave. Always learn a lot. So regarding p-values, I remember taking your class and trying to figure out what p-values mean and reading some papers that were similar to the things you've put up. Um, so I've been thinking about this for a while, and Fisher developed p-values in the 20s,
yep.
right? And then you said Name Pearson developed the approach that became in the 30s. It became very, what I can tell, became very ingrained very quickly. But then, even the papers in the 90s were saying this idea that the p-value is not a sensible thing to be fixating on. It's not new. They would cite papers from the 70s and even before.
Yeah.
So I guess, how do you know how did it? Because I can't find any information on this. How did it get ingrained so pervasively, and why has it been such a battle? You've been doing this for a long time. Miller's was doing this. The ASA is one of our largest. So hard to get rid of.
And I'm not going to blame Soakley. Did a superb job.
Yes.
It's superb. But I think that was part of it. You're right. These criticisms go back a long way. They go back to the 30s, actually. And so that's why the ASA finally doing something was a real surprise, because the statisticians knew about this. Say, oh, yeah, we know that. And they would say, yeah, we know that. But for them to do this publicly, that was the key thing. Textbooks. The Fisher textbook, which has been the model ever since, here's a technique, here's a technique, here's a technique, here's a technique, and here's a box on how to do it. Cochran and Cox did a really good job. Fisher went through 12 editions, Cochran and Cox 9 editions, 4 editions for this one. I think that's my answer to the question, what happened? It's because when you teach it, you've got to, well, students say, well, I want to know how to do this. And so we'll go, here's a box. Or, okay, what's significant or not? Well, here's a bunch of criteria. And, well, which one matters?
Okay. So even though there were a lot of papers, far more people are reading the textbooks and going to the textbooks and doing science-based textbooks than they're reading these papers.
Yeah. And when I look at the textbooks, they all have the same, they're just wonderful extrapolations on where Fisher started. Test, 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 name, 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 name. So we did one better as a key here. You get the key out of the test. And so I had a key memorized at one point in my life. So that's my guess on that one. Yeah.
Yeah, Keith, that's a great talk. I like that you thought that you mentioned in the end, something I think about a lot, kind of shifting in terms of my own perspective. It's the strength of evidence we can get from experience versus observation. And I often, I am the opposite of what you suggested in the previous slide, where we do some experiments, but master's students, 2 years, we often collect a lot of observation data and present that as evidence. We often get feedback
I've got an answer. Uh, Astronomy. It's entirely an observational science. You can't do experiments. And so, what's the basis for their causalities? And it has a lot to do with the underlying physics. We see these amazing things coming in from these, looking at far, far beyond our own galaxy or ancient uh, stars from what 12 billion years ago. They can say what the star was kind of what it was like a little bit, all based upon the radiation that's now arriving here billions of years later. So there's a way of doing observational studies that allows us to do that in a physical system. The problem is biology is not a system which stays in one place. It evolves, or we have animals that learn. The parameters move around. They're not fixed. So it becomes a bigger problem with observational studies. So then I may have skipped over it, but Delder was big on this. Make a big difference between observational and experimental. Another approach that I like is put it together. So you can't really do an experiment on a large scale. That's the perpetual problem with environmental sciences. You can only do experiments like these little tables in the room or something like that. Occasionally do something bigger. But if you embed that into a observational landscape where you're testing at high points and low points on some variable that you can measure on a large scale, then you can apply the um, mechanistic result from the very limited uh, experiment to the larger landscape rather than saying, okay, here it is, it's true, or here it is for you to think about, or here it's divorced. So the idea is to put them together. So a student with me, Joanne Ellis, spent some time doing that. One of my colleagues and I recently did something like that in landscape ecology, where we showed how you could take experiments and connect them to the landscape. So that's something that was worked out in a wonderful workshop I did in New Zealand. If we have any, yes, it's in New Zealand. Uh, and we were there for 6 weeks, and there was a nice collection of people: Pierre Legendre, myself, uh, John Grant from Dow, and two very good scientists, Simon Thrush among them in New Zealand. And we worked out that technique of Pierre Legendre produced the landscape. We then sat down, Brian McCarthy was the statistician, we sat down and put the experiments on the landscape at high and low points. What we failed to do was actually carry the mechanistic result through to the landscape again. We didn't get that far. But it was developed during a workshop in New Zealand about 15 years ago. Go New Zealand. Anything else? Yeah.
Philosophical question. So earlier you showed this sort of framework of design, execute, analyze, predict. Why did you pick the end? Don't you need to have somebody prior to your when you're designing your experiment?
Yeah, why did he put it at the end? Well, we can't ask him. Maybe Miller makes a big, I'm going to guess, Miller makes a big distinction between observational and experimental. And perhaps he was not willing to risk a prediction from an observational study until after he'd done enough observational work to really have a sense of what was going on causally. And the causal things come from not only your own experience with experiments, they come from being keen observers of what's going on around you as you do the experiment. So often you can understand an experimental result better if you are really aware of what else is happening around the experiment, including why it didn't work, but also the mechanistic things that are pinning the result. So I think that comes back to what's called natural history for the environmental scientist, understanding or at least perceiving that there's a connection here and it has something to do with something I'm going to call causal as opposed to statistics. Statistics only can measure the evidence, but there's a big argument of whether there's anything causal about them at all. And people all over the place on that. So I'll appeal to natural history. Then I think at this point, I'll turn it over to Haley.
Well, thanks for coming, everyone, and thank you, Dr. Schneider, for the great talk. And it's a little more tactical than this. So you can stop that, but also really opportunities to meet other people in biology, geared towards ecology and evolution, and to have a real dialogue with people about research papers and build topical pieces. So yeah, lots of opportunities to get together, and if you're like wondering more about these, you can ask me yesterday or ask your users guys. I'll just sort of trying to figure out what's happening in person now that most of us are all here. So we try to reach out to those things. Definitely some ways. So thanks, Dr. Schneider.